This is the Black Box Podcast. Today, my guest is Jens Groth, Chief Scientist at Nexus and a pioneer of zero-knowledge proofs. This was an awesome conversation, and I was grateful to have it. Jens helped me understand verifiable compute from a new dimension of scalable compute. It's like multi-layered zero knowledge. We break down how Scalable ZK actually works, Nexus's zkVM, the distributed prover network, and how proofs of proofs drive down cost and latency. We get into when trusted execution environments help networks and when they don't. We talk privacy without hand-waving, and we look at instruction sorting, a simple idea that might unlock another order of magnitude speed up for computation. By the end, you'll have a clear picture of verifiable computation at internet scale and how that maps to rollups, L1 design, and privacy-first apps.
You know, a founding father, chief scientist at Nexus, the creator of Groth 16. And, you know, I love zero knowledge proofs. And I know a lot of people who listen to this podcast are going to be interested because we're all talking about zero trust and, you know, confidentiality all the time. So this is a big deal for anyone who knows about zero knowledge proofs. You know, Groth 16 is it's a kind of pattern. And Jens is joining us to talk about verifiable computation at internet scale, and how Nexus is building a zkVM plus a distributed prover network to make verification cheaper, composable, and usable by rollups, and adding privacy-centered apps first. So Jens, thank you for being here, and thank you for joining.
It's a pleasure to be here, Dylan. And I'll add that we're now also working on a layer one blockchain. So we keep adding things to the stack of things that we're working on. But certainly I've been focused a lot on verifiable computation and zero knowledge proofs.
Yeah. So let's dive into that. And what you're building now at Nexus and what you're building at Nexus is also a layer one, or are they two separate projects?
So I would say that Nexus has a portfolio of different things that we're building. So we started with building a zkVM, which allows you to do verifiable computation. So basically you can do computation. You can say, here's a program I want to execute. I want to get something out of this program. Okay, now I want also a proof that this output is really correctly computed according to the program. And that was sort of like the starting point, what we built first. One problem you have with these kind of zkVMs is that they're very expensive to run. So you're paying an enormous overhead in terms of, you know, computing a proof on top of just doing the computation. And for that reason, we also built a prover network where the idea is basically you can parallelize the proving such that you can have lower latency and get the proof faster. So that's sort of like this second step. And we've been running several test nets now with millions of contributors to the prover network. And then we're now thinking about building a layer one blockchain that will sort of like basically be driven by the computation that the prover network delivers. So basically the idea is that you would use proofs to prove things are going okay and executed correctly on the blockchain.
Beautiful. So thank you for really laying that out and explaining the differences there. So I'm going to ask you a question because I think you're doing a lot, and that sounds like a lot, and that actually sounds quite difficult and challenging, I think, to most people when they're building a layer one project. I think a lot of people have stopped building layer ones, but you guys are still doing it. And the way that you are tackling the problem of latency and how exactly you scale compute faster with zero knowledge proofs is exactly what I want to be able to break down. But first, Jens, I want to ask you a personal question just so that we're all on the same page. And this way we can really understand some of your motivations. And it's just an opening question. Sometimes people answer it with like an entire paragraph. So the question's really up to you and however you would like to answer this. But what are 3 words that motivate your work? And why would you choose those 3 words?
Yeah, I think I have 2 answers to that question. So that's 6 words in total. So I know I'm going a bit above my budget here. So
Everyone fails the test.
one answer would be truth, honesty, and verifiability. And another one would be sort of like puzzles, creativity, and competition. So, and it's sort of like from 2 different angles. So the first one is really from the societal angle, right? What are we trying to contribute to the world, right? And I think, building technology that allows to increase sort of like the quality of information you get and the trustworthiness of information you get is something which is a positive sum game, right? So it's a good thing for society and for all of us to build that kind of thing. And, I would say science is perhaps an example of that, right? That we have had so much technological progress from science, basically because, well, there's a lot of thinking about how you do science, how you communicate results, how you sort of like replicate experiments and sort of like scrutinize each other's work and so forth, right? To increase the trustworthiness of the information that you have and sort of like to battle test it. So that's sort of like one motivation I have, right? It's just, I think it's a good thing for the world to build verifiable computation and make things verifiable. And then I guess a more personal question, perhaps. I mean, this is not how I started when I did my PhD or something like that, right? That was more
You
like,
said creativity. Yeah, you said
yeah,
creativity. So did it start there for you first?
exactly, right? I mean, I'm a mathematician by background. I love puzzles and things like that, right? So like having like hard problems to think about is something that's been driving me in my career, right? And I've sort of like had a taste for things that nobody really knew how to figure it out, right? And seeing if I could figure out some way to do it. And that's also a very creative process, right? So I like that, that you have this chance of sometimes you get some inspiration and you see somebody. I mean, I would say a lot of time you see somebody else has come up with some idea and you say, oh, I can also use this in this context, right? And
Yeah, researchers flexing at other researchers about how they've looked at like space cubes and thought about the equation and they're like, oh, I know how to do it better than you can do it, or just so competitive. So now it makes sense why creative and being competitive. So good choice of words. Yeah, truth, honesty, verifiability. No, this is like super, super, yeah. So societal wise, you went from like having a creative and also sort of a competitive passion, and it was entering into your life, and you found yourself probably every day, like thinking of puzzles and coming up with like answers and trying to understand solutions to things that you probably didn't have solutions to. So how in the world did it connect for you in the coming of, Groth 16? I want to understand like what was that moment, that aha moment, because I remember having some math, aha moments where I'm like, like I looked at the sky and I thought I saw shapes and I was like, oh my God, I understand, God, whatever happens in those moments, you had that moment. So I'm curious what for you?
You know what? It's sort of interesting, right? Because I think, I've been doing a lot of research in zero knowledge proofs. And I think that sort of like my own perspective on the works I've done is quite different from the public perception of those work, right? So everybody knows Groth 16, right? And, I'm very happy with that work, right? Because it's like a super compact and small proof, right? Where you can really take any big statements you want to prove and you can prove it with a few hundred bytes, right? So that's sort of like an amazing result, right? And of course but that's sort of like an end of a long journey to that, where, I did a lot of research, other researchers did a lot of contributions, right? Starting all the way back in the 80s, right? So, and I sort of like find it a little funny, whereas I think of Groth 16 as sort of like taking some ideas that were already out there, right? And improving them and sort of like tweaking them to sort of like try to get the optimal scheme. Whereas I would say that some earlier works I did, so for instance, in 2010, I published a paper which was the first pairing-based snark, right? Which is sort of like really what started the whole path of like pairing-based snarks and eventually led to Groth 16, right? Lot less people know about that work, right? But I would say that from an intellectual and scientific point of view, I thought that was a much bigger step, right? Because that was sort of like coming in and say, look, from a point where we did not at all know how to use pairings to get snarks, right? To saying you can actually do this, right? And you get these super compact proofs from pairing-based cryptography.
So would you say going from pairing-based to this is almost an evolution? Would you say, is this still involved in your work today, and how this is crafting the future blockchain that you're creating now? Is this a part of that?
I would say that I'm mostly focused on different techniques now. So the way that it works in a modern snark, typically, and in modern zkVMs and things like that, typically you used several proof systems. And the reason you're using several different proof systems is that they have different performance profiles. So, and what you want is there's several things you want to optimize, right? So you want to optimize like that the prover is as efficient as possible, right? And you also want the verifier to work as little as possible. And you want the proof to be as small as possible. And there's typically no one scheme that gives you all of those benefits. So what you want to do is instead you want to do some composition of proofs so that you sort of get the benefit of all of them. So the way that works is that you would start with a base proof, which is really efficient for the prover because that's a big bottleneck. And then that base proof, since it's really efficient for the prover, it doesn't cost so much, but it sort of like gives you something which is a proof which is smaller than what you were trying to prove and more efficient to verify than what you were trying to prove. At
It
that
verifies
stage,
almost instantly. It verifies instantly because of how small it is, right? So it's low
so
cost in terms of its size, right?
I would say exactly the opposite. It doesn't verify instantly or something like that, but it proves fairly efficiently. At this stage, you would then take another proof system and you would prove that I have a proof that would verify. But now you made the computation the verifier has to do a little bit smaller and the proof a bit smaller. So the cost of creating that proof is not so expensive. Even if the proof is less efficient, then there's less to prove, and therefore it's still an okay cost to have. But now,
is that because you are compacting both the prover and the verifier circuit together? Is that because they are effectively the same system, or they are two separate systems working in pairs with one another? I guess
let me see. So I guess the way I would say it is, think of this as a process that has several steps. The first step, you're trying to have as efficient a prover as possible and get something which is a slightly smaller and less complex problem to solve. Right? In the next step, you then use a more expensive prover because now you have something smaller that you're working on, so it's okay that it's a little less efficient. But now you want the output to be even more compressed and even easier to verify. And so you build up this kind of like chain of 2 or 3 or 4 different proof systems. And typically in the end, you would want maybe something like Groth 16 because that gives you these super small proofs, right? But the starting proof system, you don't want to use Groth 16 because it's not very efficient for the prover. So there you want to use a proof system which is very efficient for the prover. So it's sort of like this multi-process layered process where you're sort of like squeezing and then you're squeezing some more and then you're squeezing all the way down to the smallest possible thing you can have.
Yeah, that's what I'm imagining here. So I'm layering it. I'm like layering it like a cake. And so take me through that. Yeah, like this is when we're trying to frame out the problem and we're trying to measure this with our goals, which is to try to build a proof and verify low latency system that could handle real-time workloads that seem like they go through efficient proving to a more expensive proofing to outputting easy to verify outputs. You have to somehow layer this proof system of systems, like it's proofs of proofs. And I think that is one way I'm imagining it. But when you say scalable ZK, is this what you're talking about? Is the the proof of proofs. It's almost the Lord of the Rings level of zero knowledge. I don't know.
So I would say that I mean, if you look at this from an end user perspective, right? It's not so important, what actually happens there, right? But you do care a lot about the performance, right? So you want the prover to be efficient, right? So you don't pay this enormous cost that we have nowadays, right? And there's a lot of research going into making the proofs so like more efficient to compute for the prover. And then, I think the other dimensions, we've sort of like solved them, right? I mean, we can have these 100 byte, a few 100 byte proofs, right? So that's like as small as you can imagine you get, right? And we're certainly not at, any situation where that is the bottleneck anymore, right? That's the kind of thing you could easily send around on the internet, right? And the verifier, again, with these, we also have proof systems, right, where the verifier is super efficient, right, and is operating in milliseconds, something like that, right? So I think right now the game is really about how do we make the prover more efficient? And that means that a lot of the work that people are doing is basically in sort of like the base proof stage, right? That's sort of like where the prover cost comes when it gets sort of like a fresh computation and now, needs to prove that this computation is actually executed correctly, right? And we're talking about like whatever billions of CPU cycles, right? That's like a big and complex thing. And now you pay an overhead in this base proofs and the base proofs, we're talking about like an overhead of like maybe a factor of 100,000 or something like that. So it's an enormous overhead that you're paying for that, right? So all of the game from a research perspective, I think were the most interesting, so like what are the hardest problems and the most important problems are in how can we make the prover more efficient, right? How can we get it down from an overhead of 100,000 to an overhead of 10,000x to 1,000x, and nobody knows where the limit is, right? How
no one
efficient
knows. No one knows what the limit is. It's like it keeps going down its own rabbit hole, it seems like. And when you said the base computation, the overhead of having to go from prover and then to various proof systems and to be able to ensure that the prover is more efficient is effectively, does it make it faster what your work is doing? I guess what is the performance optimization that you're seeing now happen?
Okay, so I think there's a lot of ideas coming into the space. So we're seeing maybe 10x a year or something like that. There's a lot of like research going into this right now. And Nexus has sort of like been, I guess, trailing the frontier, right? And we've sort of like seen big improvements in our systems. So starting from, we could prove like, I don't know, a CPU cycle a second or something like that. And now we can do so like 10,000 CPU cycles per second on a MacBook Pro. And this is not the frontier. So there are teams that are even further ahead and can do, 100,000 or maybe up to a million, something like that. But also depending on how you count, right? Then you throw in a lot of GPUs at it and all that kind of stuff. And this is sort of like why we're also building the prover network, right? The prover network, we can do sort of like, hundreds of millions of CPU cycles per second, right? But that's because we're throwing hardware, right, and parallelizing it, right? So it's not because we have a more efficient prover, it's just because we're throwing more resources.
It's architected well. It's the fact that it can handle tens of thousands of CPUs per second. However, it's the prover network is built out as a consensus, and you're able to send a request. You can request a policy, and then you can have the zero knowledge virtual machine run the execution, and then you can have a distributed prover network that actually does the proof and or attestation of that proof. You can have those results, I'm assuming, on the blockchain. So now, what exactly is the artifact that is a developer, right, is going to end up using, or a user is going to end up seeing that could verify where do they get these proofs in this new design?
Yeah. Okay. So let me see. I think there's several things to unpack here. So if you look at it from a user perspective, you would have a program. In the case of Nexus, this would be a RISC-V program, and then you would have some input to this program, and if you run the program, you would get some output, right? And then you want to prove that this is really the output you get when you are executing this program. So you would also want to get a snark for this really being the output and not just something that the prover came up with and imagined. Concretely, that the way you specify that is that you have an ELF file which specifies the program and the data and so forth, and then you run that, and the zkVM would also take some other data, set up a common reference string as input, and then it would execute this program. So that's just basically interpreting RISC-V code. From that, it would create what is called an extended witness, which basically says this is the whole execution we've had, and so the memory accesses and things like that. And then it would run the prover, and it would generate this very small proof and attach that to the output, right? So that's the user experience you would expect from a zkVM. And now if you're running this on a prover network, right, the way it works is that you basically say, okay, look, here's a program. This is what I want you to execute. It would be submitted to our orchestrator on the prover network. And let me be clear right now, the prover network is not a decentralized, it's operated centralized by an orchestrator that takes that as input, and then it can parcel out this computation, so bits and pieces of this computation to different workers that prove, do different parts of the proof computation, send it back, it assembles that and wraps it up to be a complete proof, and that's what you send out again.
Wow,
right?
That's interesting. Wow. So you turned the prover into a network before the actual compression of that data even surfaces, it seems. So it goes through. Wow. That is really interesting. I didn't think it was that layered. Wow. But okay, so it's orchestrating through workers, and then you have bits of the information going towards these workers, and they're the ones who actually assemble the proof, but they are the prover network. Then users use those proofs from those workers, or do I have to fetch all the workers and then I can verify, or how does it work?
It would be the orchestrator that collects it from the workers backend, right? And then sends a final proof to the user, right? So from a user perspective, you're just interacting with essentially the orchestrator, or however that's represented in the network, right? And saying, here's what I want you to prove, and then this is sure, here's the execution, here's the proof that it was correctly executed.
Beautiful. So I feel like we just went over the design of how it is that the prover network actually works and how the proof goes from start to finish. And that makes much more sense. So thank you for covering the actual orchestration and the workers. That's actually really good stuff. We could keep going much deeper, especially when it comes to the layering of the proof. But I'm still curious. I want to go on to this next question to understand I think a lot of people are trying to understand these design moves that you made and the matter of throughput and the recursion / the aggregation of these proofs. So if there's a scheduler or a unit of work that is abstracted to each of these workers for the prover network to describe a proof, then how does Nexus, it's got its own zkVM, but that zkVM, I'm just going to say now, is called the orchestrator, just so that we're all on the same page. So that is
so
the same
I would
thing?
distinguish between the zkVM and the network, right? So the zkVM is something you can just run on your laptop, right? And the zkVM is open source. You can go to our website, you can download it, and you can run it. And the same goes with a verifier, right? It also has to be a verifier algorithm that can take those proofs and together with the program, together with the input and output, and check whether it really was the correct output, right, according to this proof. So this is all something you can run on just single machine. You don't need a network for this, right? So the network is really when you want to have low latency, right? So you want to parallelize the work of proving rather than running it on a single machine. And that has some interesting trade-offs, right? Because if you want to prove something via the network, right, then that network would be distributing all the data to everybody, right? So there's no privacy there at all. And that's in contrast with the original intention of zero-knowledge proofs, which was, well, we can hide everything. We don't actually reveal anything about the underlying data. We just get a proof that this was the correct output, right? So we saw like seen this kind of split in the zero knowledge community, right? That now some people are really pursuing it for the sake of scalability. Basically, you can take a large computation and you can prove that this is the output of that computation, and then nobody else needs to redo that computation because you can just check the proof that this is really the
Right.
output, right?
Exactly.
And on the other side, there are people that care about a lot about privacy, right? That want to do like identification protocols, prove that. So when I did my PhD, I was working on voting, right? So you kind of want to prove that you've voted correctly, but of course you want to do that without proving who you voted for, right? Because that should be confidential information. But if you want privacy, then you can't run it on a public proven network, right? Because then you would be sharing all your data to random nodes on the machines on the internet.
Man, that's what we're doing right now, okay? Like, I've been talking to so many different AI teams, and just the sheer matter of data that is going to open MCP routers on Hugging Face is insane. Like not enough people think about privacy. Anyway, the VM, I understand now that the zkVM is a separate.
I would say I think this cuts both ways, right? Not enough people think about privacy, but also not a lot of people think enough about the integrity of what you're getting, right? I mean, so if you're an AI company, you are outsourcing all this stuff to the cloud, say, right? And, there can also be all sorts of things that go wrong there, right? It could be either malicious, that some hackers are controlling something, right? Or it could be just that, there's a bug in a configuration somewhere, right? And you just get something bad, right? And back. And I don't know, I mean, I'm not in AI, so I don't know how sensitive these processes are, right? I mean, if you wanted to take destroy a training run somebody's doing, right? How little do you actually need to influence? Is it enough that you are controlling just one machine in the whole cloud of what they're doing, or something like that? I don't know, right? But
maybe
I would be.
That sounds about right. Like, if your prover network ends up becoming artificially intelligent, how do you prove a worker from proof of effective work, I guess? Like, how do you use your prover? I guess everyone would want to use an AI, right? Like, they would probably want an AI to at least monitor the orchestration of their worker. I'm assuming that's how the prover network is incentivized, is by running workers, right, under the orchestrator. And then when the network wants to be able to access the prover, they're actually accessing the network of workers, which could also be just AIs that run proofs effectively. I mean, that's how I see the envant of zero knowledge and like proving networks and orchestration working, is through the fine balance of being able to protect the CI/CD pipelines, and how all like network traffic is basically coordinated, and how edge computing gets kind of like fitted in, because somebody has to be able to generate a proof. I have a local machine. I want to generate a proof. I want to prove to somebody in the real world how to send money, or how to send my identity, or how to verify some information that I have personally. So it sounds like Nexus is this like universal verifier, but it could also be a prover layer that could give me, the ability to run proofs locally, while also being able to extend the computation off to the world, while it be low latency, low cost, and low cost to the prover, low cost to me in the end. And I pay, I'm assuming, in Nexus, and then I get the ledger and I get the tools, and I have ways in which I can verify. Am I on the right track here, thinking about big picture? Like, this is from what I'm seeing, how this might end up working. So that means I could write my own, hypothetically, zero knowledge virtual machine applications that run proof-wise privately with Nexus as well. So it's not a domain specific language, but it is a domain framework for writing zero knowledge proofs. Is that accurate?
Yeah. Okay. So I think we started from AI and we came to things that happen on the blockchain. There's a lot of ground to cover here, right? So first of all, I mean, people are looking at proving whether AI computation is correct, right? So you would have some sort of like maybe you would want to prove that the AI has actually been computed correct. It's not some other AI or wrong AI model that's being used or something like that. And it's a challenge because in AI, the computation can be quite heavy, right? I mean, that's why NVIDIA is such a big, important company now, because they're producing these GPUs that can handle enormous workloads, right? And since state-of-the-art zero-knowledge proofs are very inefficient in terms of creating a proof, right, then that is, for most cases, I think, an unacceptable overhead. So either we make the proofs much more efficient, right, or we just have to accept that there are other ways that you have to sort of like check whether you're getting the right things from these AI runs. There are special things that happen in AI. So for instance, there's a lot of matrix multiplications going on in AI, and it turns out that you can actually verify matrix multiplications faster than, and prove them faster than you compute them. So that's sort of like an interesting twist. So I think it's still open, to which extent we can build efficient proofs for AI computation. But that's certainly an area that people are quite interested in. I think it's also an open question. I mean, we don't quite know what the future is going to look like with the AI, right? So that's also just the question of what are actually the computations where, we need this extra verifiability, right? And what's that landscape going to look like? So we're certainly thinking about, what that will look like, right? We imagine a future with a lot of AI agents that submit transactions, probably see higher workloads and so forth, right? But it's very speculative, right? I think nobody really knows what the future will look like with AI. Right?
Yeah. No one knows. I think the implications that you're talking about are more important to talk about now. Like no one knows what's going to happen, but everyone is worried about privacy in the age of AI and how artificial general intelligence can effectively be you. It can almost be another digital twin of you. And so I think privacy, confidentiality guarantees in AI are going to make more sense. And people who I think are in the zero knowledge space, and you're in it, you're pretty deep into it, but everyone that I've met in the zero knowledge community, I would say everyone's more active in the open source mindset that, we have to be able to apply privacy to actually everything, because cryptographic zero knowledge proofs and privacy is going to save us in a sense. It's going to save us not just from AI, but it's going to save us a lot of time in building AI, because maybe what we always needed was correctness in the way that we designed an AI. Maybe that's how we could have gotten around the bottleneck of hallucination. Who knows? But I feel like there's two things. I feel like there's the mystery of how cryptography sort of helps AI. And I also think there's a mystery of how privacy actually will enable the scalability of artificial intelligence. And I think zero knowledge is almost its own revolution that's awaiting to happen again. People, I think 2 years ago, were up in arms and people were worried that privacy was actually kind of bad. Like we sanctioned it, like in America, because of Tornado Cash. So you guys are, I think, sitting in the middle, but you guys are considering the privacy implications still. Like, I know that you guys are building scalability first, and that the performance of latent, zero knowledge provability between client and user is going to be a proof of framework. But when it comes to the privacy guarantees, can privacy be scalable, right? I guess, like, what are you doing now specifically that is not only helping the scalability, but also the privacy? And how do you maintain both at the same time? I thought there were trade-offs when trying to build a system or systems of systems that were both public, scalable, and private and confidential at the same time. So what's your fine balance here?
Yeah. So I mean, so there's both a short answer, which is that there's not so much of a trade-off, right? And the reason is that if you think about a proof, right, where well, for scalability and so forth, we want proofs to be as small as possible, right? But if a proof is really small and only has a few hundred bytes, right, then there's just an information theoretic limit. It can't be leaking that much information because it's just too small to have any information, right? And it's usually very easy to take a proof which is small and turn it into also something which is zero knowledge and really leaks no information whatsoever, right? So in that sense, there's no contradiction between these two. And in most cases, basically zero knowledge is something you get for free. I think the place where there is a contradiction is like if you want to have if you have such a massive computation that you have like a proven network, right? That's what you need. Then now you have to distribute the computation, right? And you have to give shares of your secret to different entities in this system, right? And the more people you give access to these secrets, the less secret they are, right? So that's where you get into problems. But that's all at a very large scale. So it becomes more like a scale question, right? It seems to me perhaps that, if you want privacy, you will be restricted to somewhat smaller computations. And if you have something really huge, then it's maybe hard to get a private privacy preserving proof that this is correct, just because you have to spread the data to so many entities.
TEE orchestration, do you think could be a good fit for this? Do you think orchestration of how, do you think you could cover some of the privacy guarantees using just T's
Yeah,
instead?
I think it's quite interesting to compare trusted execution environments with zero knowledge proofs and all the other privacy preserving techniques. So the advantage of it at TE is, right, that it really is just a processor, right? So it runs at native computation speed, right? And it can do the same kind of computations that you could do without having a trusted execution environment. So I think and that's a huge advantage, right? And there's two parts to this also, right? One is the computation on private data. The other thing is verifying things about, somebody claims something about some private data. Zero knowledge handles the latter part. It doesn't handle the former part, right? If you want to have computation on private data where nobody knows the data, right? Then you have to use something like multi-party computation or fully homomorphic encryption or something like that. But I guess for, if you want to, if there's somebody who holds it, whether it's an open machine where everything is in the open or trusted execution environment, right, that can create a proof that this is correctly computed. So you could make any kind of claim about that confidential data and prove that claim. Okay, so anyway, that was a bit of a detour in what one can do, right? I think the issue I have with trusted execution environments is that if your trust model is somebody has physical access to the trusted execution environment and basically an attacker, right, and that wants to fool you, then I don't trust the trusted execution environment, right? So there's some people that try to build blockchains where you have trusted execution environments and you just have random people showing up with their nodes that has a trusted execution environment. Sure, you have some attestation, right? But these people have physical access to these machines, right? And when you have physical access, it's super hard to keep out the attacker, right? So I just think it's feasible for them to break into these machines. So I would see the role of trusted execution environment much more being in the situation where you actually do have an organization where you have some control. So imagine you are a big tech corporation, right, or something like that. You already do some vetting of your employees and so forth, and you can set up monitoring of physical facilities and things like that, right? And I think in that kind of circumstance, maybe a trusted execution environment is something that gives something more, because it's hard to actually get the physical access to carry out an attack for these people in this organization, right? And if you don't have the physical attack, right, then access to it, then I think it starts to give you something.
This basically did some wiretap research, demonstrated a vulnerability in
Mhm.
Intel SGX on DDR core platforms. And so Fala had to recently announce to everybody that it's been making a state towards next generation CCC, which is using TDX instead with NVIDIA confidential computing. So why is that important? Because you're absolutely right about the physical problem. I think TEEs have a problem of decentralizing the hardware. That's been the problem. And I know that this is exactly what Flashbots and Nethermind and also Near Foundation, what they're interested in is how to, I guess, decentralize the framework that allows us to host the confidential compute, right? And so TDX has been used now, I think, as sort of the next step. It's the preferred choice, the method, right? that everyone is going to end up using. There's also AMD SEV, and there's all sorts of different types of STEs, but the one that you're discussing is mainly related to SGX, and that has been used for blockchains. And there's a lot of stories and dark stories that go down that rabbit hole, but it's quite hard to pull off the attack regardless. But with SGX, you could do it with you could just do it with AI now. It's literally extremely easy, and it's not surprised anymore that we're gonna have a huge problem, especially if people are using old deprecated SGX software, which is a problem. I could totally see why you guys don't want to choose it, obviously. But TDX is safe, right? AMD is still safe, technically.
So let me be clear. We have nothing against trusted execution environments. I do think it has its role in certain circumstances. You just have to be very aware of what is the threat model it can resist, right? And I think zero knowledge proofs have a very different threat model that they can resist than trusted execution environments, right? So that just means that there are sort of like different spaces where they work best, and also opportunities for complementarity, right? You may have the sort of like the collaboration of these technologies.
Yeah. So the collaboration of the technology. This is actually one of the questions that I gave you, because I was like, you know what? The moment that I ask you about like anything TEE related, I knew you at some point were going to bring up FHE. So we have to ask the question, what if you combine TEE, ZK, and FHE together, right? Isn't that just the perfect system? Like we're just mixing and matching all these terms anyway. So why don't we just use all of them? Why is that not the most optimized way to scale, I guess, like public verifiable compute? Privacy leaks are creeping in constantly, like, because that's the whole problem with zero information, like as you were describing before. So ZK solves a lot of things in terms of correctness. FHE seems like it solves a lot of things in terms of being able to trust native compute. And then TEE allows for some kind of trusted orchestration. So between ZK, TEE, and FHE, when you're thinking about it, what do you draw the line between, running this something in a TEE to make it attestable, proving something in zero knowledge, you making it publicly verifiable, and then going all in using FHE, which I think can increase the level of privacy, but it also increases the costs. So do you think that these three together are going to end up being the final result? Does it not look like this in your mind?
So not done research on FHE myself. I've used fully homomorphic encryption in one of my scientific papers, but so like as a black box tool where I didn't really look at the inside of what was going on there. My understanding is that fully homomorphic encryption is still very inefficient. So basically it's too expensive to use for many of the applications. There might be some like variations of that. Sometimes you don't need fully homomorphic encryption. You can use something called somewhat homomorphic encryption, which doesn't allow every computation, but it allows some computations to be done, and that could be more efficient. So there's a lot of trade-offs and things that people are using here. So, and the goals are different here, right? So in homomorphic encryption, what you want to do is basically you want to put on encrypted data, right? Which makes a lot of sense from a privacy perspective, but also it's expensive, right? And another technique that covers some of the same space at JFHE is secure multi-party computation. There, your trust model is that you have several nodes that are collaborating to compute something. Some of them may be evil, but not all of them. So, assuming that there are not too many of them that are bad, then, your data is secure and confidential. And again, you have some performance overheads when you use secure multi-party computation. The zero knowledge base in some sense is sort of like a more narrow domain, right? Because we are just concerned, we want to make sure that something is verifiable. So you can make a claim about something and then you can prove that the claim is true. And I think, if all of this worked ideally, if all of this was efficient, then sure, we would just use that. And it's not clear we would even need a trusted execution environment, right? Because everything would just be secured by cryptographic means.
By cryptography
And
alone.
reality is just that we are so far from there. Right? So we need to come up with different intermediate techniques, right? Which and you have some trusted execution environments which are good for some things and I think insecure in other things. So and I think sometimes people misunderstand which things is secure and insecure for and put too much trust in them, right? But on the other hand, for the kind of things that they can do, right? It's another tool. Just as we've also had other things that we needed to do trusted, right? Where we just you hire somebody who you think is trustworthy, right? And you trust them to do something for you.
Like I'm going to be trusting Nexus to roll up my data, for example. So I want to use it so I can prioritize like cheaper, more universal verification. That's why I would use Nexus. It sounds like I could use it for like maybe I make my own privacy centric application and I build the privacy, but then I just leverage your provability and the verified compute layer. And I do all the privacy, on my end and do all the FHE for my user on the front end. So maybe there's a different way of thinking about it. You're right. There has to be like, I think all of them are used. I think all of them are used to some degree, but they're not used to solve one whole complete problem. Let's move on. The zkVM inside of TEEs, right? Like we've done some experiments with this and, I think there's just some interesting information that I think people would want to hear more about from the zero knowledge proof side, which is like two things. Like you have a lot of experience building with zero knowledge, like why build with zero knowledge with circuits, not like with, interpreted language sets. Like, we on the TEE, we have to build everything. It could be front to back end. But when it comes to building with zero knowledge, what is the preferred libraries, methods, systems that you're using to build appropriate zero knowledge from your perspective? How does it look like to build a zero knowledge proof? What are you using to build with this? What are the systems that you're using now to build these?
So the programming, we're mostly using Rust. Also, it wouldn't be fair to say we're just building, right? I mean, you pull in, crates and tools and libraries that others have built. And in our latest zkVM, we are definitely relying very heavily on Stu from Starkware, right? As sort of like the backend for our proof system. So, but I guess there's a critical piece here, right? Which is sort of like, why would you trust this piece of software, right? To actually give you a proof, right? So why should you trust that proof? And I think so like, well, what are the standard strategies now? I mean, it's open source. You can principle inspect it, right? But if you don't have a PhD in cryptography, then that's probably not going to be that helpful to you, right? So then you can have audits by third-party companies, right? But then you are, of course, trusting these companies and so forth to catch bugs, right? So there's a sort of like a big effort going on now, supported by the Ethereum Foundation, to actually sort of like really use formula verification tools to verify the source code of a proof system. So I think that is one thing that we will hopefully see more of in the future. And this is especially on the verifier side, that you want to verify that piece of software that verifies the proof is really working correctly, right? I mean, it matters less to verify the prover, because if the prover makes a mistake, then it'll output a wrong proof, and then the verifier will catch that there's something going on, right? So it's sort of like, there's some things you wanted to prove that fail, but that's sort of like a more benign failure mode than, here's a proof for something, and then it turns out that it was actually false. Language and people construct, program in various programming languages. So that's sort of like something which is we're quite agnostic about. So I would take a step back and think of this from a theory perspective, right? I would say that, okay, what is a proof system? Well, it has to have 3 properties, that if what you're trying to prove is actually true, then it should be possible for you to prove it. If what you're trying to prove is false, then it should be impossible to prove it. And then the zero knowledge property that, the proof should not leak information about the private data that you use to prove something. And you can so what is a good verifier? It's just that one which is willing to accept correct proofs for true statements and on the other hand always catches somebody who's trying to prove a false statement. And if you go into what are the techniques that are used for this? So you're right about this is a bunch of math, because typically what goes on under the hood is, suppose, for instance, okay, I have a program. I want to prove that this program executed something correct. Right? There's a number of steps. So first of all, you would compile that to, say, a RISC-V program, whatever the language is that the zkVM supports. Now, under the hood, then in the zkVM, you would then basically write this the whole execution. So you would record the first step, I read this register, and the second step, I read this memory, and then in third step, I added 2 numbers and blah, 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 right? And you can imagine just recording this whole, what you did in every step, right? That is what is called an extended witness. And basically, that this is a correct execution that yields the output at step 1 billion or whatever size of length of the computation is, right? That you can write down as mathematical equations. There's a mathematical equation that says from this state of the program and, these data, then this is what the state should be in the next step. And with these data in the next step, this is what should be the situation and state in the third step, and so forth, right? So now you have this enormous...
So this is called extended witness testing, right? Extended witness testing, or how do you define this?
Yeah, so this would be the extended witness. And then these mathematical equations with that, basically constraints. So in the zkVM setting, you can write down a fixed number of constraints that ensures that this is the correct transition from one cycle to the next CPU cycle, right? And then you just have billion repetitions of these constraints, right? On different parts of this whole execution trace. And it turns out then, and this is a very common theme, is that when you have constraints where you have a lot of repeating patterns, then you can often use randomization to batch them together and make it more compact what you want to prove. So basically you can think of what the verifier's role is, in some sense, is to give you some random challenges that allow you to glue these constraints together and compress them to something smaller.
So that means the proof already came with the constraints, and then what the verifier is using, they're using the compiled prover's constraints to then challenge you as the client with those challenges. So what you're proving is proving location too, locality of that the proof was generated by not only this system and this machine, but this algorithm or this compilation target in a sense. So the verifier also verifies the system that you're trying to prove with as well. So system-wise, RISC-V verifier can never work for a RISC-0 verifier in a sense, because of the way in which challenges are presented and the way in which constraints are constructed. Is that another thing to be cautious of, aware of?
So it is. It's true that the verifier is tied to one specific type of statements or claims that it can verify, right? And if I want to verify something and it turns out that whatever you do is related to something completely different, right? Then a completely different machine, then I cannot tell you whether that's computed correctly or not, right? So that you're certainly tied up to what you're trying to the system that you're operating on. That's just the verifier is specific for that type of architecture, and this is also one of the parameters that you can then be working on as a researcher. You can design different instruction set architectures, right? And some of them may be more amenable to facilitate easy proving and easy verification. People have been saying. So as an example, RISC-V has 32 registers, but some have designed zkVMs that have, where the instruction set architecture only has, say, 3 registers or something like that, right? And then, if there are less registers, maybe it's easier to verify some things about it. On the other hand, maybe the computation is a bit more cumbersome because there are only 3 registers to work with. So there's a lot of these kind of trade-offs that people are exploring.
We never know. So like when it comes to for rollups and for the priority of effectively making the design cheaper, the amount of universal verification that you have to do for this type of work, I understand now why you're using Starkware as the proof system and why you're going with open source audited third-party systems so that we can be able to formally verify that our systems are secure. There are formal verification tools that you recommended. I didn't have any down, but it sounds like Ethereum's foundation is actually making it so that researchers have an easier time building cryptography and what is a proof system, and there is effectively no leakage. I like that. You said that private data is private proof. So if there's no leak, then you're good. The beautiful thing about like proof systems like Groth is that it can almost compress information to a small sets of bytes. And you can only verify what you catch. You can verify any correct statement, any incorrect statement, and you can compile these steps to a zkVM. You can read from the registry and you can record what's on that registry using extended witnesses. And this is a type of test, and in terms of zero leak, that means the input information was embedded within some structure, right? I don't know, like some structure, right? Some construction, and it could be anything, but so what I guess in terms of these structures are important now today and not yesterday. So I'm curious, like zero knowledge is evolving as quantum computing is evolving because quantum cryptography is meeting zero knowledge. And now we're getting the onset of AI. What does it look like to be using AI, building zero knowledge today? It must be exciting. It must be like crazy next steps, right? Like you're doing some groundbreaking research probably faster than you were before years ago. Now with AI, plus the research in quantum, plus now what you're doing with zero knowledge, what is the most efficient thing that you're seeing happen now, I guess? Like what are the patterns and the things that you're excited about?
Okay, so let's see. So if I understand your question correctly, it's sort of like, what does research look like now? And also what is sort of like the impact of AI on the research and sort of like how you work as a researcher. And yeah, so I guess at this very moment in time, I think AI is not strong enough to do much for cryptographic researchers. I mean, there are all these kind of bold claims about, and AI is like, PhD level in all sorts of things. It's not PhD level in cryptography, right? So it's not going to be that helpful. So what we're seeing in the space right now is basically, human researchers trying to come up with new ideas, and we've seen so like many different techniques that people are trying. I think we're seeing much more that people digging in more and more to details. Right? So like, back in the 80s and 90s and zeros and the tens, right? We had all the low hanging fruit. So we sort of like did that. Right now we're sort of like really digging quite deep, I think. So people are, using a lot of mathematical objects. So finite fields would be one mathematical object, and you can sort of like decide, do you want to use a small finite field or a large finite field? And they have sort of like different trade-offs. You can ask what kind of commitment schemes, how can I log in some data that, the verifier should later verify is unchanged. And then again, people experiment with different kind of commitment schemes. Some of them are quantum resistant, some are not quantum resistant. So there's a lot of like, this kind of work going on. And then I guess, my experience with AI so far is, it's not really good for cryptographic research. It is, I would say, getting to a point where it can sometimes dig up some, say, mathematical literature that I was not aware of, right? So it's sort of like starting to get to the point, and it can sometimes, spot that you have made an error. So, again, there's a lot of hallucination, but once in a while it catches something. So I do think that there is sort of like small tasks that it can help me with, but it's not like at a point where it's really like, a research assistant or a PhD student or something like that. But then again, 1 year from now, I would not be surprised at all if that's the case, right? I think the development is so rapid in AI. So I think it's definitely going to come in and impact the research that we do in zero knowledge, as it is going to be in all other places, right? And it's quite interesting then to think about, okay, what would be the impact for us, right? So there's been sort of like discussion. I mean, okay, so why do we build a zkVM? So there's another approach, which is so like, you just build, so like here's what you want to do. You just build like a special purpose circuit that can, handle this specific thing, right? And the zkVM is more saying, well, you can just build something general purpose. It's going to be a bit slower and more inefficient, but you could take any program and you can just compute it so it's easier to use, right? And so there's these kind of trade-offs. And I'm wondering if some of those trade-offs will be really changed. Will an AI really be programming in so like one of the programming languages that we're using today, or will it come up with some different approach? And maybe so like with AI that can handle more complexity, maybe it can design circuits directly and so forth. And it's something that we're thinking about, like, is there an opportunity as well for us to build this into the zkVM? Might be things that, can be sort of like optimized by AI as it comes in on the fly. And then the question is, how do you verify and make sure that it's not hallucinating, but it really is correct, right? So maybe you combine that with, some formal verification techniques, which AIs can also do, right? And then you are actually guaranteed that it's not bogus, but it really is correct what it's doing.
That's like zero knowledge machine learning, right? Like you could use proofs and epochs,
Yeah.
right? You could prove that training was done correctly, I'm assuming.
Yeah, so I think this would not be a training run. Again, I would say that training runs are sort of like outside the scope of what we would be able to do efficiently anytime soon. So this would be more inference at compile
Inference,
time.
eval, right? Like what the weights were. You could prove the weights, you could prove the eval, you could even prove context. You could probably prove prompts. You could prove simple things, but you're right. Maybe not fine tuning. That would just be extremely, maybe just expensive, but I'm following you. The finite fields, the commitment schemes, but what is the day in the life of being at Nexus? What does it look like? What is this Nexus on a daily basis? Is it coffee in the morning or?
I think it's so like a constant change and new directions and new ideas and a lot of energy that goes into it, right? I'm not sure I want to claim that we are different from other startups. I think that's sort of like a very common startup experience, right? You're trying to sort of like you make something maybe very complex work and play together, right? And there's a lot of challenges, and sometimes you just have to take a new direction, and then that's what you're going with, and so forth.
I think the whole team at Nexus is making grounds, and you guys are figuring out this year proof, verify latency, cold starts, memory footprints. I saw somewhere that you guys are figuring out how to do network throughput. So you guys are building a network, and what guardrails and supply chain steps, I guess, like, are you guys thinking about reproducible builds or version pinning or revocation? I guess, what ships with Nexus, right, by default? Because there's a lot of teams that start their network. So I guess, like, what's the first thing that you guys are going to, like, prove and verify with the world? I guess, is there going to be a demonstration sometime soon, or what's the first thing that you think the community is going to be able to get involved with in your guys' work?
I mean, we've already had some tests that's out, right, that were trying to prove different things. And one was sort of like a small AI training run that we were verifying or proving. So you can sort of like see that more in our blog. We have stories about the different kind of things that we have already proven. But that's, it's still sort of like in experimental phase. Ultimately, I think we will be sort of like powering our layer one blockchain via proofs. So there, a lot of it will be so like with, inbuilt support for proving that transactions were carried out correctly and so forth. Right? So like want to optimize for verifiability on the blockchain. There's still quite a lot of work that we have to put into that to make it all come together.
but it's huge. Verifiability is, I think, the biggest anchor in terms of establishing trust in AI. And I think with verifiable workloads, you could be able to prove that locally the computer had executed a specific program, a specific computation faster and cheaper, but then you could verify it in a decentralized way through Nexus and then be able to verify it on chain. I'm very bullish on being able to verify anything trusting. And that same sort of zero trust architecture like thinking is being able to verify everything from the ground up and including like economics. And you guys say here in the blog, like you want to be able to transition the world into a safe sort of AGI future. And your blog is actually discussing the crosshair between AI and economics. So that makes a lot of sense. And you guys definitely have an interesting sort of roadmap. And what one milestone would convince, I guess, like a skeptical rollup builder, the person that's coming to Nexus is either going to be a privacy builder, rollup builder, or what else? Like what do you think is going to be the main utility for Nexus in the foreseeable future? Because how I see it is that it could really help bolster DeFi, because if you could trust computation to both a proof and verification network, it's much easier to create more of like a trustless AI that manages economics in a sense. And so maybe that's what your guys' pilot program is like, or
Yeah, exactly right. I mean, you can certainly verifiability is super important in DeFi. So that's an area that we are very interested in. We would also be interested in other areas, like say traditional enterprise sector and so forth. We think can also give something. I think in blockchain space, I mean, people are so used to having public data, so there it's okay that we are sort of like focusing on scalability in other contexts. People we've been talking to have been sort of like quite interested in privacy, right? So, and what will really convince people to use it? I don't think it's one thing. I think it's more a question of a package. I think it's so like, I mean, there's so many teams building in zero knowledge. I think we are so like, going to evolve, and get some good technology. I think, I guess the next step would be so like, what does it mean that a system is mature, right? And comes together and it's actually something that people can use. And I think, it's so like ironic, right? That zero knowledge is so like, very good for building trust and doing trustworthy computation, right? But it's a challenge for us, right, to actually convince others that it's trustworthy, right? So there's also just the work that goes into that, and that maybe that's the kind of thing that will convince people. And there's a lot of things you can do, so like to build something which is mature and reliable, right? I mean, obviously,
yeah.
we're open sourcing things. We have documentation out there, right? We'll have security audits, a lot of steps along those lines, right? That you can use to build trust in the software that we're building.
Yeah, scalable zero knowledge is more than just having faster proofs. It's a end-to-end verification experience where all the artifacts from the developer are going to be ending up to be cheaper. They can be checked and they can also be private, and it's intentionally private and it's not accidental. So where do we go next? I guess everyone should definitely go and look and read the Nexus white paper. The zkVM 3.0 just recently posted with Groth's talk on how memory checking and the verifiability vision is presented in that paper, all with the reproductions and the proof and the check pipelines. So you guys recently proved the prover. You checked all the memory. Where is the zkVM right now? You guys just released the white paper. I would love, this is my last question, but where is the zkVM now? What's the next step? And what are you guys currently kind of working on? What are you stuck on? Is there any way that people could help you?
So, I mean, so we've released the version 3 of the zkVM, right? So that's open source and the kind of things that people are running in the test networks that we have up and running. And one thing that we are going to sort of change in the next version is that we're going to do so like what is a technique known as instruction sorting. So basically the idea is that right now we have like there's a bunch of instructions in RISC-V, and so like have constraints that guarantee that they're correct. And as we go along, so like the whole execution, we apply these constraints. However, then you're actually constraining too much because you're using some of the constraints because this was an addition operation, right? But then you have useless constraints that, if it wasn't an addition, but it was an XOR, then this is what you would have constrained. And there's a technique to sort of like instead try to compartmentalize the kind of things that you're doing. So we're thinking about moving to something called instruction sorting, where you sort of like sort by the type of instruction. So you take the execution trace out of order, not in the time sequence it actually was executed, but instead you sort of like put it into buckets that these are all the additions these are all the XORs that we're going to do, and so forth.
That's so
And
okay.
and then you can basically, for each of those buckets of instructions, right, then you can have a simpler constraint system, and that will save some of the proof efficiency. It's not clear how much that's going to give us, right? But I'm certainly hoping that we'll have so like in maybe close to an order of magnitude or something like that improvement.
Wow,
So that's
that's
going to be
really
exciting.
cool. Yeah, no, that is really exciting. And who would have known that it's all comes back to when we were 3 years old, when we were putting big orange cube in big orange basket, and then big square cube in big square basket.
Yeah.
It's like that one meme of the guy who's like trying to fit like a square peg in a round hole, like like that ended up being the true zero knowledge solution, guys. Orders of magnitude faster for just simply freaking sorting it. Just sort your operators, guys. Just sort your operators. It's so funny. That's so funny.
I think it's so funny. I've never been on a podcast before where somebody said, "Oh, you're basically doing the work of a 3-year-old."
Yes. We finally did it, guys. I made it, Mom. That's awesome. Well, John, okay. You are incredible. Thank you so much for describing everything that you described today. And I think there's some research that we all have to do, a little headhunting. We did some research today, but the next thing on my list is going to be instruction sorting. So I'm interested. And your time. Thank you for coming to this podcast. This is the 6th episode. This is going to be rolling out next in a couple of weeks. So this is right before Tech Week ends. So we're here in San Francisco. And so for anybody on October 31st until the end of next month, go check out Nexus. They're going to be having some really awesome events happening next month. We're going to be involved. I'm going to be there. We're going to all make it, I guess, or we're all going to be there. So thank you for your time, for your presence, for your information, and please, thank you, everybody, and take care.
Takeaway: ZK proofs can be layered, compressed, and networked to scale. Privacy holds until secrets spread. TEE, ZK, and FHE each solve a different part of the puzzle. Follow Nexus for zkVM updates and visit follow.com for the latest in confidential compute. Thanks for listening.